Thank you all for coming out. It's 5 o'clock at Vmware World. Usually do not get this level of attendance in spite of the registration, so I'm thrilled with that. That's awesome. So I am Brett Garino. This is Rebecca Fitzhugh. We'll be giving formal introductions as we get to each section of the session. I will be doing the CPU portion of this session, and Rebecca will be handling the memory portion. This is compute. So we're talking about vSphere performance troubleshooting root cause analysis. Okay, this is for the compute, and then we have another session that we do. It's going to be happening tomorrow that is on I/O, which is network and storage. So if you're intrigued by that as well, feel free to look up that session too. Okay? Now, as we get into this, we initially have the disclaimer, and you guys can read that. So I'm Brett Garino, and I'm a principal instructor at VMware. I work in VMware Education Services. So when we talk about troubleshooting and root cause analysis, though, I do just want to point out, primarily this session is going to be focused very heavily on key performance indicators around CPU and memory. So actual counters and their thresholds and what you should be looking at and why and how you should react to them. Okay? And we will be primarily looking at ESX top as a means of doing so. So if you're very comfortable with this topic already and this is something that you do all the time, you may not get as much out of this session. If you are new to this tool, you're going to get a whole lot out of this session. All right? Just want to level set and give you guys all the proper expectations as we go into this. But that's who I am. I teach. I'm also a VCDX. I'm VCDX 256, and Rebecca will give a formal introduction herself whenever she gets to it. Now, before we actually talk about CPU, when I hand off memory, before we actually talk about CPU, we're going to talk about ESX top, because this is the tool that we want to be using to analyze our Core 4 resource analysis. Right? This is a phenomenal tool. It's built into every single ESXi host. And that's part of what makes this so valuable to you. Because no matter what customer you walk into, they have this tool available for you to use. And there are a few tools that are as comprehensive as ESX top. Now I will tell you, the only limitation of this tool is the fact that it runs in real time. Now you can run it in batch mode, and you can have it actually record some data, and then you can replay that data later. However, it does not, by default, show you anything historical. Right? So if you're having an issue, this is a wonderful tool to use. It's my favorite tool to use if I'm having an issue in real time. If I'm looking at historical analysis, I might look at logs, vCenter server performance charts. I might go look at other things. Right? But this is not a tool necessarily, unless you were running it in batch mode when the problem happened, that is going to give you the opportunity to look at anything historically. So with that being said, how do I run ESX top? ESX top is going to be, it's the command. Okay? You go into the shell of an ESXi host, which you can remote into it using PuTTY, or you could use iDRAC or ILO, whatever you want to get into the host. You could have a KVM locally. But as long as you can access the shell of the ESXi host, you can run the command, ESX top. If you use a tool like VCLI, you'll have to use RESX top. But ESX top, if you're local to the ESXi host, is exactly what you're going to run. And this is not what you're going to see when you do that. What this is the help screen. So I always tell everyone, there's two things you need to learn ESX top. This and the command name itself. Now, as you go look at the different screens, and we've highlighted several of them up there, C for CPU, M for memory, there are 3 storage views. Okay, we'll cover those in that session tomorrow, and then we have N for the networking view, which will be covered in the session tomorrow. But CPU and memory is what we're going to zero in on. As you navigate these different views, always be mindful of the fact that the help screen will have different and unique options potentially on each view. So you need to familiarize yourself with that as well. Now, moving into actual CPU key performance indicators. As we look at this, we point out and we start with ready time, utilization, and load average. And those are for the ESXi host. That's on the left-hand side, highlighted in the blue box. In the green box, we've got virtual machine indicators. So we have ready time, co-stop, swap wait, memory limited. Okay, we'll be exploring these in more detail. But the first thing I want to tell you is, in troubleshooting, we need to recognize a few things. Number one, why are we having this problem? If it's performance related, it's because your consumer is asking for more than what your provider can give. On this screen, your consumer is on the right, the virtual machine. On the left, your provider is the ESXi host. That host is responsible for giving the resources to the VM. It's when we run VMs with more allocated resources than the host has physically available that we tend to run into performance issues, because we have oversubscribed CPUs or over-allocated memory. and we exceed the actual physical resources that are available on the box. So, provider, consumer. And I'm going to highlight this as well when we start looking at the screenshots of ESX Top, because that's how you need to be thinking when you approach ESX Top. In addition, the hypervisor is an abstraction layer. It abstracts the physical hardware resources that are on the box. So what that means is we have the virtual machine consumers sitting up here, their guest OS is above that, and the applications above that. Everything originates with the application making the request for CPU or memory, and then has to pass through the guest OS, subsequently pass through the virtual machine hardware layer where we have individual hardware devices such as vCPUs and VRAM, and then that passes through to the VM kernel, subsequently to the actual hardware local to the ESXi host where we actually make the request of the physical hardware, if it's available. So when it's not available, what happens? We get latencies, the counters get worse, and these are the metrics that we use to identify when those things are taking place. And we have to be able to recognize whether the problem is a VM or a host. So, moving forward, we look at using RESX Top interactively, or just using ESX Top interactively. Wherever you see RESX Top in these slides, you can substitute ESX Top. I just use the remote command if you're using VCLI. So, we point out you just enter C or M to access the CPU or memory pages. And remember, H is going to let you see all of the options within there. So if I run ESX Top, this is the default view. It's always going to start with CPU as the default view when you run the command. Now everything above that gray line is your host, your provider. Everything below that gray line is a consumer. Now, the consumers are not just virtual machines. There are also services that keep the ESXi host running, such as host D, or something relative to logging, or it could be something relative to the I/O injector. There's a bunch of different services that run on the ESXi host. So as we analyze this, one of the things that we want to be able to do is truncate the view down to just virtual machines, unless I'm troubleshooting a resource contention issue, maybe with a host service, which is unlikely. Typically when I come in here, I'm looking at virtual machine to ESXi host resources. So we can limit the view to just show virtual machines. Currently, this view is only showing me services. That doesn't do me any good if I want to see the virtual machines themselves. So above the line, you have the ESXi host physical resources. And what we can see on this host is you've got the timestamp going from left to right. We have the timestamp, and then we have the number of worlds. Okay? Now, worlds are groups of services, like process trees. Okay? So a virtual machine is composed of a variety of worlds. Every vCPU you give to a virtual machine is another world, so that you can analyze the vCPU's performance independently. Because sometimes you might be having a problem where a virtual machine with a dozen vCPUs is only using 3 of them. We would want to react to that if we were seeing that kind of behavior. So, as we look at this, we have the number of worlds, and then you have CPU load average, which is highlighted in the red box. And there are 3 numbers. The first number is the last minute of load on this ESXi host. The second number is the last 5 minutes, and the third number, it's either 10 or 15 minutes, I'm not sure. It's one of those 2. But it's more historical than the 1 or the 5. So what we can see here is the trend on this is that this host has gotten extremely busy, and it's in CPU contention physically. Okay? We want that number to be 1.00 or less, generally speaking. So in this case, the fact that it is 2.0 plus is very bad. Okay? I would expect to see some negative CPU counters as a result of this. So, as we look at the numbers, we have CPU used. That's a wonderful metric that tells you how much of your CPU is spending its time actually functioning and doing work. A lot of times, your CPUs will be idle. Idle is not necessarily a bad thing, okay? One of the highest numbers you're going to find on most of your virtual machines that aren't very busy is, in fact, idle. Because when vCPUs aren't busy, we park them in an idle world. So, on the right-hand side over there, I believe that is ready. Yeah, it's hard for me to see from here. So we've got ready up there, and ready is something that we're going to be talking about. That is your primary key performance indicator for CPU. Okay? So we'll talk about what ready means as we go into this. First off, I want to introduce you to the CPU co-scheduler. Now, there was a time in VMware's history where if I created a virtual machine with 4 vCPUs, and I only needed one of those vCPUs, we had to send all 4 and schedule them concurrently. Okay? This is when we had what was called a strict CPU co-scheduler. We have not had this since ESX 2.5, I believe. However, the idea persists in many circles that we still operate this way. We don't. So what we have instead is a relaxed CPU co-scheduler, which means if I create a VM with 4 vCPUs and in this clock cycle I only need one of them, only one of them will be scheduled. The remainder will be scheduled to an idle world. And this sounds great, right? It's idle. That doesn't cost me anything, right? We'll learn about something called co-stop in just a bit that informs us that idle is not always the best thing. We want our virtual machines to be right-sized so they actually use the resources we give them. So, this is the CPU co-scheduler. And if you were to Google for that phrase, you would find a white paper that I ripped this out of that is based on ESX 5.1. This shows you the various states that a CPU can be in. And this is invaluable to understanding how the CPU works and functions and the different counters that the CPU could be experiencing as part of its normal functions. Okay? So, when we start this off and we have a new CPU operation, it can go to run or ready. Run is ideal. Run is calculated as part of used, which we said earlier that used tells you how functional and how used the virtual CPU is. So run is ideal. I want my virtual CPUs to be running as often as they'd like. But what happens is we increase consolidation ratios on the boxes. Right? We put more virtual machines on them, and we give the virtual machines more resources, and inevitably we create conditions where there are more vCPUs than there are actual cores on the box. And this leads to CPU contention, which can ultimately lead to scheduling issues for the CPU, which in turn can drive values like ready. Ready is a metric that indicates that my virtual machine's vCPU wants to run, but it can't. We'll talk about why not in just a bit. Co-stop is a metric that we'll talk about in more detail as well. And that helps you to determine when your virtual machines have been given too many vCPUs. So in the process of right-sizing virtual machines, I can use ESX top to help me make that determination. Or maybe for many of you, you have vRealize Operations Management, and it tells you when it's time for you to resize a virtual machine, which is wonderful. But what if you wanted to actually go validate what it finds yourself? You could use ESX top to do so, because the metrics that it uses to make those determinations are the same ones we're going to be looking at here. So weight, although it's red on this slide, is not something that you generally have to worry about. Okay? Weight values are generally pretty high on virtual machines that are idle, and we don't worry about that too much. I don't know why they opted, when they authored this paper, to make weight red. It makes you think that it's bad. It's really, I really don't pay much attention to weight. There is a metric called VM weight that includes I/O overhead of processing network and storage I/O within the virtual machine, and I do pay attention to that if it's excessively high. But we don't cover that in this session. So just something to mention. So the CPU scheduler is responsible, the relaxed CPU co-scheduler, to call it by its actual name, it is responsible for scheduling vCPUs against physical cores on your ESXi host, or logical threads that are represented atop the physical cores. If you're hyper-threaded, you have 2 logical threads per core. Don't schedule against hyper-threads. Avoid it if possible. All right? I try to never build a single VM on a ESXi host with more vCPUs than I have physical cores to give on the box. Okay? So, but the CPU co-scheduler is responsible for determining which core on the box a vCPU should be mapped to for the operations. And that's an important thing, because if you think about it, what happens if I move from core 0 to core 1 and I'm currently a virtual CPU? Do I still have access to all of my last layer cache, my layer 1 cache, the cache that's on the processor? This can impact memory operations on databases and things like that. So when we're looking at migrating vCPUs, the CPU co-scheduler is responsible for making that determination, and it does so with a decision-making process that occurs every 2 to 40 milliseconds. So it's constantly migrating vCPUs if necessary, but it prefers to leave them in place whenever possible. All right? Now, a world, we said earlier, is like a group of services. Every virtual machine is made up of worlds. You have the MKS world, mouse, keyboard, screen. You have the VMM world, the virtual machine monitor, which is a resource that every single virtual machine resource request has to pass through. So every CPU request, every I/O request, every memory request actually has to pass through the VMM. And then you have your CPU world. And there are other world types that we're not going to cover in here, but you're welcome to look at them inside of your ESXi hosts when you're using ESXtop in the CPU view. Your virtual machine will have additional vCPU worlds for every single CPU you add to a VM. And you don't see them by default on the screen. You have to strike the letter E on the keyboard when you are on the CPU view and identify the identifier of the row, which is a numerical value, generally 6 or 7 characters, numbers long. And after you actually identify that, it will expand to show you all of that virtual machine's worlds. Why is this important? Because if I see a virtual machine that has a high ready value, it could just be on one of the vCPUs, whereas the other vCPUs could be doing nothing. Well, that indicates a problem, right? My virtual machine should be trying to use all those other vCPUs. So that's why it's important that we recognize the different worlds and our ability to expand and then roll up the worlds so that we can see all of the worlds that make up a virtual machine. So now we're going to talk about co-stop, okay? And co-stop is a metric that is only going to be above 0 potentially on VMs with more than one vCPU. So you have to have what we call a VSMP-enabled virtual machine, which is virtual symmetric multiprocessing. Couldn't even get that out. So if you have more than one vCPU on a virtual machine, you potentially will see co-stop greater than 0. This is a metric you want to always be 0. When will it not be 0? Well, if you've given a virtual machine too many vCPUs, and the virtual machine is not using all of its vCPUs, then co-stop will increase as we have to engage in co-stop operations. What is a co-stop operation and why does it happen? When you have virtual CPUs on a VM that are actually running and virtual machines vCPUs that are being scheduled to the idle world, as that takes place, skew is being generated between the vCPUs because one of the vCPUs is advancing and running while the other is being held behind. When this skew breaches a certain threshold, and I frankly don't know what it is, but you will have a co-stop event. Okay? So when the CPU co-scheduler recognizes that the skew breaches a certain threshold, a co-stop occurs. And what that does is, for an entire clock cycle, we do not let any of the vCPUs run. They are all halted in unison to reset the skew back to 0. You can't process when this is taking place. This is why it's important to right-size your virtual machines. So when, relative to co-stop's findings, should you go and reduce the number of vCPUs on a virtual machine? The answer to this is we generally want to see co-stop lower than a value of 3 in ESXtop. And if co-stop is greater than 3 in ESXtop, then I seriously need to consider reducing the number of vCPUs on my virtual machine. It will likely increase performance when you do so because you will have fewer co-stop operations and more opportunities to run the vCPUs on the box. When we look at additional CPU performance factors, idle virtual machines. Okay? You could have idle virtual machines. You've probably heard the recommendation. And we tend to think that idle has no cost. Idle, of course, has a cost, right? We sometimes call these zombie VMs or vampire VMs because they just sit there and suck resources and they're not doing any work. So we want to mitigate idle VMs in our environment, and we want to make sure that we don't leave hardware devices on our virtual machines that are not necessary because you have timer interrupts. And we pull those hardware devices in the guest OS, and that requires CPU utilization. Leaving things like screensavers running inside of virtual machines wastes CPU cycles. So we want to take that into consideration. CPU affinity is something that will pin a vCPU to a physical core. This is never a good idea. Okay? There is no reason I've ever seen to do this in a production workload. Okay? So you literally pin a vCPU to a physical core on the box. This reduces the efficacy of the CPU co-scheduler. You do not want to do that. Let the CPU co-scheduler do its thing. It's faster than you will ever be at determining which core should be in use. SMP-enabled virtual machines. If I have those, which we all do, those are virtual machines that have more than one vCPU on them. I need to make sure that I'm monitoring those for co-stop metrics. Okay? If I have performance issues on a virtual machine with lots of vCPUs, I'm going to jump in ESXtop and I'm going to zero in on co-stop and see what the metric is. And if we have insufficient CPU resources for the demand, how does that happen? It's because we've allocated more vCPUs on the box than we have physical cores to give. And ultimately, what that results in when those vCPUs are attempted to be used is the fact that CPU ready time will go up. Okay? So, when we're talking about CPU ready time, as we get into this, we want to take, and you can see we've got ready up there as a metric on the right. When we talk about CPU ready time, we haven't really explored this specifically, but CPU ready time is when your virtual CPU is requested and the VM kernel refuses that vCPU request access to the physical processor in this clock cycle. So latency starts creeping up. And the ready time is going to be increasing in a metric of milliseconds to reflect how long it's been since the vCPU requested physical CPU access until it actually gets it. Okay? Now, this is represented in ESX top as a percent of CPU time. So as a percent of CPU time, you generally do not want to see CPU ready greater than 10 for any singular vCPU on the machine. Now let me take this back to our discussion earlier about worlds. If a virtual machine has 4 vCPUs, if it has a ready value of 20, then I need to expand those worlds. It's not 10 VM wide. Okay? Ready should be 10 or less per vCPU, not VM wide. Okay? So we can expand and roll up those worlds. And what we want to make sure that we do when we expand and roll up those worlds is look at each vCPU's ready value. When I look at the whole virtual machine, the ready value is 20, and the VM has 4 vCPUs, I might expand it and see that each vCPU is at 5% ready. Now, that could be indicative that a problem is going to come, but we're not doing so bad right now. But if when I expanded those and I saw the 4 vCPUs, one of them was 20 and the others were 0, I have a problem. Okay? So, when we look at the CPU metrics here, we're looking at, this is one where we've got 2 virtual machines running. We've isolated the view to only showing virtual machine consumers below the line. There are no ESXi host services visible there. So when we do this, you can see, starting from the left, there's the ID, there's the group ID, there's the name of the virtual machine, which is a friendly name that you are familiar with from the display within your vSphere client, your HTML5 client. And then you have the number of worlds. If I was to strike the letter E here, it will ask me for the GID of the virtual machine that I want to expand. And then I can see all of the vCPUs within there, as well as the mouse keyboard screen world, some network analysis worlds. We've got several different world types in there, the VMM, all of those worlds we were talking about. But you'll see all your vCPUs, and that's what you want to be using here. Okay? Now, ready time, we had talked about earlier. I kind of jumped the gun on that one, but I felt like it was the right time. So, but ready, once again, just to recap, vCPU is requesting access, and the VM kernel gets in the way and says, no, you're not allowed access. But remember, that happens because we have scheduling contention because we put too many vCPUs on the box, and they're all trying to be used. All right? So, how do we mitigate ready time? Generally, we don't even have to worry about this because you have DRS in your environment. And as the host contention increases, DRS is going to migrate those virtual machines and load balance them so that we generally never have to think about this. But this is for when you have those VMs that you're trying to troubleshoot the issues on. So when we look at percent used and percent ready, as we can see on the screen here, we have those columns listed on the CPU screen. Okay? And ready, remember, if you see the value VM wide because you have not expanded the virtual machine yet, don't get concerned if it's above 10 until you've expanded the virtual machine. But generally, your ready value should be 5% or less when you're looking at ESX top. Okay? When you look at ready inside of the vCenter server performance charts, it's going to be represented in milliseconds. Okay? And this is really confusing because when you go look at it, the interval that is sampled for the performance charts in vCenter is 20 seconds. Well, there's 20,000 milliseconds in 20 seconds. So when it gives you a ready time in there, you want to take it as a function of whatever the value it gives you. Let's say it's 1,000 for ready. If I see 1,000 milliseconds, I'm thinking, my vCPU was sitting idle for a full second? No, it was 1 second total out of the last 20 seconds. Okay? So keep that in mind when you go look at vCenter server performance charts for these same metrics. Because you can find all these counters, most of these counters, inside of vCenter server performance charts as well. So here we actually see this in the web client. And what we're showing here is usage versus ready. And this is an ideal state right now. where usage is the blue line, ready is the yellow line, and I want to see ready low and I want to see usage high. So that's exactly what we have here. I want to see lots of utilization, very little ready. So here we look at the viewing of single vCPU information. And what we've done here, this is the expand and roll up that I was talking about earlier. So we see this visually. When I strike the letter E, you can see the group to expand or roll up. And then we enter the GID, 182331, I think that is from here. And you can see the GID is repeated for each row for that virtual machine. And you can see the VMX World is in the second row in the bottom graphic. And then you have VMX Thread, and you have VM Test. And that bottom one is the ones that you want to be paying attention to, where it says vCPU 0. The next vCPU would be vCPU 1, and so on. On a VM with 8 vCPUs, you would have 0 through 7. And those are the metrics you want to be paying attention to. So here we have our host saturation. What do I do if my CPU on my host is saturated? Well, it's because of my consumers, right? If I have the ability to just vMotion virtual machines off, I want to try that. If I have DRS in my environment and that didn't already happen, maybe I need to manually try vMotioning some of the VMs causing contention, and I may find out that they've got hardware devices that are preventing them from doing so. Okay? So if the host utilization is greater than 75%, you need to relocate the virtual machine, turn some virtual machines off. There's no magic bullet to stop this. Okay? If you overallocated resources, you have to shuffle the load around or scale the resources up on the host or get the virtual machines moved off to another one. Okay? Whoops, let me go back there, sorry. And then we say that, if it's not, then go back to your basic troubleshooting flow. The ready value we point out down there, that should say 2,000 milliseconds or 10% for any vCPU. 2,000 milliseconds is 10% of 20,000. So if you're looking at this from the GUI in the performance charts, that's why we represent that value. In ESX top, you're looking at 10%. So here we point out what you can do to resolve host CPU saturation. Reduce the number of VMs on the host. Increase the available CPU by adding resources to your cluster and then vMotioning the virtual machines off. Increase the efficiency with which virtual machines use CPU resources. What we mean by that is reducing the number of vCPUs on the virtual machines when you use costop as the metric to indicate that you should do so. And finally, use resource controls to direct available resources to critical virtual machines. That is a suggestion that you use reservations to guarantee CPU to certain virtual machines. If you're not familiar with reservations, I suggest that you read the resource management guide for vSphere. And this is going to get us to Rebecca's portion of the discussion, which is memory.
I must say, I've known Brett for 12 years, and this was the hardest 28 minutes of my life to not crack a joke on his behalf. So I'd like to think I'm the hallmark of professionalism right this second. By the way, if no one's ever told you your voice goes up in pitch when you're lecturing, you kind of sound like Danny DeVito in Always Sunny in Philadelphia. So, getting into memory, if your brain hurts a little bit with all that CPU metrics, I promise you, I chose memory today because memory is far easier than CPU. I did not choose CPU on purpose. I let that guy run his mouth. So, my name is Rebecca. Unfortunately, I know this guy, and somehow we've gone this far without presenting together, so we thought, why not? So here's basically all the ways that you may contact me or harass me out on the internet. And as you can tell, based off of my About Me slide, I'm far more accomplished than him.
Guilty.
Honestly, I hate this guy. I don't know why I'm up here right now. So, memory.
We worked together way too long.
Way too long. So when you get to ESX top, all right, so as Brett showed at the very beginning, it's a set of quick keys to navigate the different menus. Memory, you'll never guess what you press. You press M for memory, and you will get here. And this shows you quite a bit of information right off the top. So first thing we see on the right is the high state. Okay? And we're going to get to that in just a second, what high state means. But this is an indicator of the state of the host at that moment. And this will, without even looking down at memory metrics, will give me a good idea of what is happening. Okay? And what we see on the other side of that, to the left, is going to be our memory free. Okay? So this is exactly what it sounds like. How much memory do I have free? And then further left to that, what you're going to see is the P memory and the VMK memory. So P memory is how much memory you have physically installed, and then the VMK memory, this is the amount of memory that is being controlled and managed by your VM kernel, or ESXi itself. Now, notice that there's a difference. We're losing, in this case, something like 20 meg. Where does that 20 meg go? So this is something that I personally like to call Brett this. Sometimes it is a PCI hole. And the PCI hole is memory that gets allocated for your PCI devices, right? For your different network devices and storage devices on your ESXi host, okay?
It's necessary.
To call you a name. So if you see to the right of that, you're going to see the min free. Right? So in this case, it looks like something like 244 is min free. Now, I'm going to press next, and min free will make a lot more sense. But what min free is this is a variable based off of how much memory you have installed that effectively determines what is the minimum amount of memory I need for ESXi to function. Because ESXi needs memory as well, right? For it to have the ability to schedule things with the CPU, for it to be able to respond to I/O requests, and so on. So ESXi does need memory, and we have to determine how much memory that is. So variable based off of what is installed. Does anybody in here have 4 gigs of memory installed on their ESXi host? No, right? So for most of us, when we start looking at, okay, I have, 256 gigs of RAM installed on your host. For the vast majority of people in here, it's going to be 1%. Okay? But the lower the memory, the higher the percentage. Okay? So when I hit next, we see a lovely chart that lays out what's going to happen at different states. So on the previous slide, we saw that we are on a high state, which means we're pretty good. Okay? We're pretty good to go. Now, as we obviously start getting lower and lower and lower, right? So we go from clear, high to clear, clear to soft, soft to hard, and then low. When we're in a low state, this is basically nothing else is going to consume memory. We're going to start blocking all memory requests. Think of it as your host going, hold on, if I don't have memory, then I can't have these virtual machines running. And what happens when your host runs out of memory? It's going to crash, right? So this is absolutely starting to block all new requests from memory, and it's swapping, it's compressing, it's basically doing everything at that point that it can to effectively survive. Okay? This is a huge indicator that there is obviously a memory problem, and we need to determine what that is. So there's a lot of things happening right here. So we start talking about transparent page sharing. Okay? So think of transparent page sharing almost as, if you will, deduplication from memory. Okay? Realistically, if we're running 100 VMs on one ESXi host and they're all Windows, the same version, don't we think that there's a high probability that there's several pages of memory that are exactly identical across all of those 100 VMs? And then would we also assert that that's probably not the most efficient thing for every single virtual machine to have its own unique set of pages that is exactly the same as another VM's set of pages? That doesn't make a lot of sense, right? So we're going to share those pages of memory. And obviously that is very configurable as to what that scope is for sharing and whether or not you even do transparent page sharing. Now, a key thing to keep in mind here is that most of our modern guest operating systems use large pages, right? Large pages of memory. So instead of it being very small, as you can imagine, your page of memory could be up to 2 megabytes, right? Instead of in the kilobyte range. And so with that, one of the first things that we would try to do to save memory is share, right? Share memory. What is the likelihood if I have, say, a 4 kilobyte page of memory that is going to be the same as another 4 kilobyte page of memory? It's pretty small. It seems like a pretty high likelihood. Whereas on the flip side, if I have 2 pages of memory that are 2 meg, what is the probability that they're exactly the same? It's a lot lower, right? Because there's a lot more data in that set of memory, right, in that page. So what we'll do at the very beginning is we'll start breaking up those large pages into smaller pages to increase sharing probability. Right? That doesn't sound too terrible. And then as we start getting in there, we start getting into ballooning, compression, and swap. Those are a little bit more complex, so we have slides dedicated to them. Right? So ballooning, compression, and swapping. So we take for granted transparent page sharing a lot of the time if it is enabled. We take for granted that it is happening. And so one of the things that we look for when there are problems are these 3 metrics. Okay? And these are going to be indicative that there is a problem. And here's where it gets really easy. Brett spent all this time going, oh, well, for this particular CPU metric, it's going to be 3. For ready, it's going to be 10%. For memory, it's pretty simple. If everything is functioning, I shouldn't have ballooning, compression, or swapping. So if everything's good, everything's healthy, I should go in and just see a bunch of zeros. So if I'm seeing anything greater than 0, that's an indicator that there's a problem. Told you memory was easy, right? Class dismissed. Okay? 0. That's what we're looking for. So getting into ballooning. Ballooning is one of the first things that would happen, right? Should we start experiencing CPU contention. And ballooning, a very important thing to call out here. What differentiates ballooning from the other two, from compression and swapping, is this is happening within the guest operating system of the virtual machine. This is not happening at the hypervisor level. Okay? The hypervisor is the one experiencing contention. Right? It is the one who's running out of memory. But what it does is it actually invokes something called the balloon driver, or you can see the lovely name up there, VMMEMCTL, or Virtual Machine Memory Control. And this is a driver that is a part of your VMware Tools installation. So if you've installed VMware Tools, you have the balloon driver, right? Pretty simple. And so your ESXi host is going to target virtual machines, and it's going to say we're going to basically balloon it, right? I need some memory back, effectively. And so what the balloon driver does is it creates artificial, if I hit next a couple of times, artificial contention, if you will, within the virtual machine. So now the virtual machine believes that it's running out of memory. This seems a little bit counterintuitive, but hear me out. This actually makes a lot of sense. So now your virtual machine is going to swap. Now this is not hypervisor level swapping, what I'm going to talk about in just a second. This is happening within the virtual machine, and it is swapping to, if this is Windows, its page file. And that page file is located, of course, in the VMDK, right, in its virtual disk. So it's going to go ahead and page out to its swap space. And then over time, right, the ESXi host will give memory back to the virtual machines. Now, I said that this is not necessarily a bad thing, right? Us creating this artificial shortage, if you will, of memory. And here's why, right? This is really the key differentiator between ballooning and the other things with compression and swapping. This is in your guest operating system. I would argue, and this is the one thing I might say something nice about Windows in my life, is that your guest operating system probably has a better idea of how it's using its memory compared to the ESXi host. Your ESXi host is servicing requests. It doesn't necessarily, even though it's running hashes obviously on the memory in order to share, it's not necessarily popping it open and going, what exactly are you doing? So you may have memory that to the ESXi host appears as active, but it really isn't. Okay? And so your guest operating system, though, knows that because it's your guest operating system that's actually using and allocating that memory to various processes within the guest operating system. So the advantage of this happening before anything else, when you're running out of memory, is that your guest operating system is involved. And so who in here thinks if the guest operating system gets to choose what pages of memory get swapped, is immediately going to go, you know what we should do? All the active memory first. No, that's counterintuitive. That's dumb. And so when your guest operating system gets involved, it's going to, of course, say, you know what, I'm actually not really using this memory for anything. We don't need that. Well, look at this. This page of memory hasn't been accessed in quite some time. It holds data, but we're not using it actively. Why don't we swap that out to our page file first? Right? So it's going to go through and free up memory that's free, not currently being used, or idle before it ever touches your active memory. That's pretty important. Okay? That's the key differentiator here. Okay? Because when we start getting into compression, this is happening now at the hypervisor level. And so it is targeting memory, and it's going to take memory and it's going to compress it in a cache stored in memory. So it's compressing memory in memory. Now again, this is quite smart because if you think about it, what is the alternative? Well, I think you already know what's coming next. Hypervisor level swapping. So with hypervisor level swapping, what are we doing? We're targeting pages of memory and then saying go out to disk, go out to that vswap file stored on the data store. What do you think is going to be more efficient? Swapping a page of memory out to disk to the vswap file and then potentially having to swap it back in? Or compressing a page of memory within memory and then decompressing it within memory? I'm going to argue memory within memory is always going to be faster than memory to disk, regardless of the type of disk. So it's really going to go through and it's going to identify those pages of memory and it's going to compress them. And we're going to get about 50% savings, okay, give or take. It's not an exact science, but it's about 50% savings. So how much that is going to vary on the size of the page itself, right? Because we already mentioned that that is a bit variable depending on the guest operating system and the size of page that it requests. Hypervisor level swapping. Who in here has experienced swapping? How fun is that, right? It is so much fun. It's my favorite thing to never experience again, right? And this is where it becomes really important to highlight that we've got ballooning occurring, right? We've got transparent page sharing occurring. We've got a compression occurring. All of these mechanisms are occurring. And then your hypervisor is still running out of memory because either we're not doing our jobs, we haven't looked at our monitoring tool, we're not seeing these alerts, maybe we've got DRS misconfigured because, as Brett already mentioned, DRS should be looking for these things. It will be looking for these things, and it's going to remotion your virtual machines away from that hotspot. If we get all the way to this point where we have to swap memory to disk, to use a very dated YouTube reference, Honey Badger don't care. Okay? It's going to just pick pages of memory and swap it to disk. So there's really nothing stopping the ESXi host from grabbing active pages of memory and going, you, go to disk, potentially before free, right? Or even potentially before idle, because it is doing it at random. So the goal is, because we saw at the very beginning, we've got all these different states, right? High, clear, soft, hard, low, to catch this way before it gets to the part where we are swapping, right? So that way we don't have to experience our memory swapping out the disk and potentially swapping back in, because that's not very fun, right? Disk is just not ever going to be as fast as memory. So it is important that we are, of course, monitoring this, and these become our key performance metrics that we want to be looking for. So on our memory screen, this is the one negative thing I'll ever say about ESX Top, because like Brett, I do have an affinity for this particular tool. They don't have ballooning by default when you go to the memory page, okay? That's important. But it is a metric that is in there. So for you to see ballooning information at the guest operating system level, right, per VM, on ESXi, with ESX Top, you do need to hit J. And J will actually basically bring up a menu that shows you all of the metrics that are available, not just the ones that are there by default. And then you can go through and select ballooning. And it's going to then give you
It's F.
F.
J is the option inside of the F menu.
See, that's what I get for looking at the slide and seeing J and being like, that's the thing. Thank you, Brett. F.
I did it in my last session.
F, yeah. So F for the fields, J to select. And that's going to give you the ability to see your ballooning drivers, or your balloon driver, whether it is installed or not, and whether or not you are actually ballooning. So again, right up at the top, before we even get into per VM, you're able to see, right, our physical memory installed, how much the VM kernel is managing, but you're able to see things like swap, zip, and then memory control, right, so ballooning. And that's giving you the aggregated amount at the hypervisor level. Okay. So we do see what it is currently, so 633, what the target is and what the maximum is. Okay. So in this particular example, if we look below, we start looking at our virtual machines, and we go to the right, we see all of these different counters, right? All of these different columns. The first one we see is memory control question mark. Is the balloon driver installed or not? This is also a nice cheat, if you will, a life hack on quickly determining whether or not all the virtual machines on this ESXi host have VMware tools enabled, right, and installed. Because I don't think any of us are going to install VMware tools and then purposely drill down and find the balloon driver just to disable it, right? So we're going to make the assumption here that you've got VMware tools installed. So notice in this particular case that only 2 of my virtual machines have the balloon driver installed. So when we kind of quickly look over, all the way to the far right, our memory control max. This is the maximum amount that I can balloon. So I can quickly kind of add those together, and I am terrible at math because, like Brett, Louisiana, and scroll up to the top, we see that it says 1267 is the maximum, right? And looking at 633 plus 633, that seems reasonable, right, for that to be the maximum there. So it's just simply adding those 2 together. So our memory size, this shows us how much memory is configured per virtual machine. And this comes into play right over here when we start getting into the maximum. So notice that for our virtual machine, it has 988 meg of RAM installed. And to the far right, we see that we have a maximum of 633 that we can balloon. What is a very interesting thing with ballooning is that ballooning at most steals 65%, if you will, of the memory away from the virtual machine to preserve itself. A maximum of 65%. So that means, worst case scenario, if the balloon driver is as inflated as it can be, and I'm taking as much memory as I can from that virtual machine, that it still has 35% physical memory, right? Whereas when you start thinking about swapping, the hypervisor will swap 100% of a VM's memory if necessary, right? So there is a threshold here. And then we can see that we have targeted a particular virtual machine, and it has experienced balloon activity, and it is actually maxed, right? So in this case, the virtual machine 02 is experiencing ballooning, and it is maxed out. It's ballooned as much as it can possibly balloon. Kind of the easy way to always think about ballooning in a way is it's robbing Peter to pay Paul, right? So we are kind of taking a little bit from the VM to preserve the ESXi host. Oh my goodness, so much. All right, so the last one on here that I haven't discussed is the one that I mean, Brett, what do you call it? I call it touched. I don't know what else TCHD is supposed to experience there. So this is the active memory, okay? This is active memory. So this is basically the pages of memory, the aggregate amount of the pages of memory that this virtual machine has most recently accessed or most recently touched at the hypervisor level. So this is what the ESXi host is presuming to be active memory. To pause for 1 second and go back, you know what I ideally see here if everything is awesome? I see that I have the balloon driver installed on every single virtual machine, and then when I start looking over, we'll know what the max is. But then when I start actually looking at the target and what the actual balloon size is, the goal is to always see nothing. I want to see zeros across the board. That is a good sign for me. Same thing goes when we talk about compression, right? I can also see this at the very top when it looks like the zip, right? This shows us how much memory we are currently compressing on the ESXi host at an aggregate level. Then we can also drill down to the particular virtual machine and see the cache size, right? So now we know how much memory we have per VM that is cached, and how much we have that is compressed at that point, right? So how big that compression cache is versus how much we are actually compressing, and then how much memory is actively being compressed and decompressed at that point. Right, so zip, unzip. You'd never believe that zip would be the short, right, for compression. Again, I'm telling you, I cheated here. I picked memory because this is easy. Threshold that I'm looking for, 0. I want to see 0 compression. That's what I want to see when everything is running and healthy, right, which is exactly what I see here. So I'm pretty happy with that. The next thing is swapping. You would never believe what the metric I'm looking for here is as well. 0, right? I want to see absolutely no swapping whatsoever. But we may absolutely experience swapping. So again, at the aggregate level at the ESXi host, I can see what it is currently and how much I have reclaimed because of it. And then I can see how much is being actively swapped, right? Swap read and swap write. And then I can also, of course, see that per virtual machine. So we can see how much swap space we are currently using. Right? So to kind of pause for a second, if we do not know, whenever a virtual machine is powered on the data store it creates a vswap file, right? And the size of that vswap file is the size of configured memory unless you have a reservation. Because if you have a reservation on your virtual machine, that means it's guaranteed to have that much physical memory all times. Therefore, why would I ever swap it? I wouldn't. So in the case that you have a reservation on your virtual machine, it would be then configured memory minus reservation equals the size of your swap. All right, so that is your vswap file that you will see at the virtual machine level. And again, this is created at power on for the virtual machine, and when you power it off, does it really need its swapped memory anymore? No, it's off. So then you're going to have the vswap file get destroyed at that particular point. Okay. So swapping activity, what do I want to see? Nothing. But here's the fun thing. And this becomes very apparent in the I/O session tomorrow as well. All of our resources are fairly interdependent, right? One doesn't really exist without the other. And so I'm actually on a CPU screen, and I'm still talking to you about memory. So if my virtual machines do not have enough memory, there's possibility that there's also going to be now CPU repercussions because of that. Because I cannot actively process whatever thing I need to process because I don't have the appropriate memory in place as well. Because again, CPU and memory are very interdependent. So in this particular case, we see some virtual machines are waiting 93% of the time for CPU resources because of swapping. Because swap activity also uses CPU resources to swap in, swap out. So now, because of a memory issue, I'm experiencing potentially some CPU issues as well. So that would be another key indicator as well. How do you fix contention? Right, because that's what we're describing here. I am describing experiencing host level contention. Well, to be perfectly blunt, There's really only a handful of ways. A, you reduce the amount of overcommitment. Maybe you've overcommitted simply too much, right? You may need to go ahead and reduce the level of overcommitment. So the easy way to do that is spread the load, right? Migrate virtual machines off. But realistically, if your entire cluster is overcommitted, you simply vmotioning a VM from one ESXi host to the other is just moving the problem, right? So then you need to look at increasing the capacity of the cluster itself, okay? You may not be ballooning, all right? In a perfect world, I never experience ballooning. But if I have to choose to experience ballooning or to choose host level swapping, I'll take ballooning, right? And I'm looking for now ballooning to occur, and that's going to be a key indicator that I need to start looking at how to address this and solve the contention problem before it becomes worse. So easy way, right, to prevent swapping is to simply install VMware tools. Maybe you just need more memory, right? And then of course, reservations. Because think about this. If I reserve 100% of memory on one virtual machine, in a way, I'm kind of screwing over the rest of the VMs. So we better make sure that that one VM is really important and it really needs it. And more importantly, if it does need it, that we've appropriately sized the reservation. Because you oversizing that reservation now means that in the time of contention, I can't take or borrow things back from you. And if we're talking about ballooning, these may be things you're not even using to begin with. So that means every other virtual machine out there, I'm going to have to take a little bit more, right? So we want to make sure that we are absolutely either A, not using reservations if they're not necessary, or B, if the reservation is necessary, we do need to make sure that it is appropriately sized. And it should be the minimum amount here, right? What is the amount of memory that I absolutely need for this operating system and this application to function in a worst case scenario? And then the last thing is very counterintuitive. What if this is happening at a virtual machine level and this is not necessarily at the host itself? What if I have a single virtual machine experiencing these? Now, this could be because of a limit, whether at the VM level or at the resource pool level, or simply I haven't sized this virtual machine appropriately. So I may need to configure more memory or potentially have a small reservation, okay, if it is experiencing it at a per VM level rather than at the host itself. And with that, we covered a lot of material very, very quickly, but we wanted to make sure we left a few minutes at the end. So please, if you have any questions, we're happy to address them. Just make your way to the microphone so we can have this on record.
Before we have any questions, just want to point out, please fill out the survey. So just a reminder for that. And we'll be happy to take any questions. If you've got to run, you can find both of us on Twitter. I'll be happy to answer any questions there. I'll be in the Education Lounge in VM Village tomorrow from 12:30. Starting at 12:30, I'll be there for about an hour or two. So if you have any questions, you can catch me then. Sorry, I'll be quiet. Go ahead.
Okay, great. I have a question regarding the worlds that make up a VM. Mm-hmm. What exactly is the VMAST world for? VMXT?
VMAST.
Vmast.
One of
your screenshots.
I frankly don't remember. I'm not going to lie to you. I used to know it, and I have no idea anymore.
Isn't Vmast
Do you remember?
overhead?
It's Vmast overhead, but it's I
thought it was the overhead for the actual VMM itself.
Well,
I could be wrong.
Is Vmast the VMM?
I could be wrong. No.
Yeah, I don't want to lead you anywhere. You get with me after the session, and I'll get you an answer, and I'll send you an email.
Okay, great.
Yeah.
Another quick question for Rebecca.
Uh-oh.
I don't know whether it was Photoshop or stuff like that, but is there any particular reason your hosts compressed or swapped in a high state?
Those are super old screenshots. Okay. So the chart that we showed you is the newest chart. There were, and this has changed and evolved since 5. And so 4 to 5 to 6. And so if you actually look back at some of the older, these are old screenshots. So if you actually look back at the old tables, there was no clear state, things like that. So it's just modified over the years.
Okay, that's actually an excellent question, and I'm gonna dovetail into that. You can have an ESXi host that's in a high state that has swapping, ballooning, and compression on it. Okay? What this generally means is that these things took place historically. So let's say a host goes into contention and we migrate a bunch of virtual machines off with DRS. You never witnessed the contention, but you go in ESX top and you start panicking. Boom. Well, I see all these metrics for swap and ballooning. What it is, when we do that, we don't, when the contention subsides, we don't pull the memory back out into physical RAM. So we leave it there, and if it's necessary that we need the memory, then we pull it out.
All right. Thank you.
Yeah, that's part of why.
Hi, thanks for the session. I have 5 questions. There's a big line.
You want to come up and we'll talk about it? If
Yeah.
do you have time now?
Yeah.
Great. Then come on up and we'll talk about it. I mean, everyone else just has one?
So yeah, I'll
Okay, yeah. I want everyone else to benefit from it, though.
Yeah,
so if you don't mind, come on up. Well, I'll let you use the mic too for the next. Go ahead, sir.
Yeah, just for the clarification. For the best performance in terms of CPU, should we turn on the hyper-threading or turn it off at BIOS level?
There's an interesting Intel security thing going on with that. I think that was hotfixed. I don't remember though. I'm not positive. So it was temporarily disabled. Hyperthreading was disabled on one of the recent updates. Hyperthreading for performance should always be enabled for performance, but given the security risk, that comes first. So I think we're past that. Anyone know? Anyone want to chime in? We are. Okay, thank you. So you should have hyperthreading enabled. There's no reason to not have hyperthreading enabled. The key thing is don't build a single VM that has to be scheduled against the hyperthreads. If I have 20 vCPUs, I don't build a 40 vCPU VM or anything over 20. That's the key thing.
Thank you.
Thank you.
Hi, so I have a question about in our environment we're running into issue where we're using SRVs, so we're running VNFs, right, for NFV. So we're running into issues where it's actually a KB article where you get alarms for high memory utilization when technically the guest OS says it's running fine, but for VMware in the GUI it says, hey, your memory utilization is very high. So my question is, would going through the CLI of doing the ESX top, would it also show in that section a false reporting of high memory? You showed a slider captured there, I remember previously. Would that also show that, or?
You want to go first?
Well, if you're talking about memory, I'll let you do it.
Go ahead.
You're the memory.
Ladies first. So you're talking about at the guest virtual machine level?
Yeah, so at the guest level, everything's fine, but when you're in the UI section, the alarms, you get multiple high alarms that there's high memory. So there's a bug for like 6.5 where it's a heuristic, I think, memory trigger. I don't have the actual key.
The reason I was trying to pass this off to Brett is
It's okay.
I was going to say something not quite so nice about VMware. So realistically,
You're at VMware.
I know. Realistically, when it comes to the utilization of the virtual machine's memory itself, who knows better than the guest operating system, right? So your ESXi host might think that there's more active memory than there actually is, because it might have been memory that was recently active but is now idle, and so it may be basically kind of giving you a false positive because it's gathering that over a period of time if you're looking like in the vSphere web client over a historical period. So that's not necessarily reflective of what is happening in that guest operating system at that time, because your guest operating system is basically actively using pages and making it idle in real time.
Because we're
You want to add on to that?
Yeah, I'm just going to follow that with, I think your question was, and I'll just repeat it to be sure, in the GUI you're seeing this alert, but you're asking if in ESX top the metrics would match.
Would the message match?
No, the metrics in ESX top are going to be what's actually getting used.
Okay, so that would be.
And you can suppress the alert. I don't know if that's a good idea, or you could change the threshold so that it's, but.
So that would be a good workaround if you're saying in the actual CLI using the command.
Using ESX top, you should see what the actual utilization is, but she's right about that TCHD thing. The touch memory or the active it's an approximation. It's not a guarantee. What's in the guest is what's real.
Yeah, because we're reserving all guest memory because of the PCI pass-through and all that.
No, that happens. No, there's valid use cases for that.
Supports back is to basically disregard it or clear the alarm.
Yeah.
Do you want to cut that there?
Oh wow, I didn't even realize we had another one over there. Yeah. Well, we have one more. We'll do this very quickly.
So you said that memory and CPU are interconnected in the performance area.
Yeah.
So my question is I/O and CPU is also interconnected?
Yeah, so actually if you come to the session tomorrow, that's not, I mean, it's intended to be, yes, come to the session tomorrow, but also realistically, like if you're experiencing high latency on, like, for example, the disk, you're naturally going to have resource utilization on the host increase because of it, right? Because if that, for example, I/O is not getting issued out to disk, where is it happening, right? So you're going to have queuing happen, obviously on the adapter level, and then potentially even within the hypervisor itself, and that can increase the utilization, right? So that's, one example of disk I/O issues potentially creating CPU. Right, issues.
If you run out of memory, when compression starts, you're burning CPU cycles. When ballooning and swap starts, you're increasing network utilization, you're increasing disk I/O. So when you lose one, it generally will impact the others. Yeah.
Okay, thank you.
Thank you.
Just a quick question. I work in healthcare, and a lot of the VMs always want to have specific memory reservations. Is there anything in ESX top that could say, because they always want the super high end.
You're saying the vendor wants a ridiculous reservation.
Yeah, always.
Yes.
There's some, like a quick command that I can say, you know what, you really don't need 64 gig of memory, you only need 16. Because we run into that all the time.
Yeah, it's not just in healthcare. There's tons of vendors do not understand, tons of software vendors do not understand virtualization, and their answer to eliminating this as a potential issue for them is reserve everything. Now, in spite of the fact that that's horrible for the ESXi host and everything else on there.
Self-defeating in a way of virtualization.
Yeah, so your question though is there a way that you can give a reservation without giving a reservation?
No, just through ESX top to see, what, they don't really need 64 gig of reserve memory, then they only need, 32 or 16, or is there some sort of...
If you give the reservation, you gave the reservation.
Yeah, I mean, you can always look at, at that point you kind of want to, I would say, correlate data between something like ESX top and the guest operating system itself, right? Because then you're going to have, from the ESXi host perspective, if you look at like touch, how much memory it's, from the ESXi host perspective, actually touching at that moment, and then you can correlate that back over to the guest operating system and see how much memory the virtual machines in the operating system thinks it's using at that point. And you're going to be able to go, okay, on average I'm seeing this, at max I'm seeing this. So for example, you might go, at max I'm only ever seeing 8 gigs of utilization. Why do I need to reserve 64? Right? I mean, that's what I would do, and that's what I've done as a consultant. I mean, that's not the perfect answer, but it is kind of looking from both perspectives of the hypervisor and the guest itself and figuring out what is going to be appropriate.
Awesome. Thank you so much.
Of course.
Thank you.
For the transparent page cache or
transparent page sharing,
does that occur when there's no contention, or is it?
When enabled.
If it is happening, is there any kind of like performance impact? Should I be overcommitting my memory because of it?
That is a great question.
Workload dependent.
It is, yes, completely workload dependent. So it's going to happen regardless of whether you overcommit or not, and that may give you a little bit more flexibility in terms to be able to overcommit a little bit more. Right? And by no means am I going, go overcommit times 12, right? But it does give you that flexibility based off of how homogeneous or heterogeneous that particular, your workloads are, okay? Now with that, it is always happening, and then the second part of your question was about performance impact of that occurring. And that is a very, very good question, because guess what? It uses CPU cycles to do this, because it's going to effectively run a hash against the memory itself to make sure that the hash values come back to be equal. And that's going to give a hypervisor the go-ahead to say, yes, those 2 pages of memory are 100% the same. You can share them, right? So that way we don't basically screw up your guest operating system. Now, is there overhead associated with that? The answer is yes and no. Right? And that's not the best answer. Yes, this does use CPU cycles. Does this create or basically increase your CPU utilization? Not really, because this happens during CPU idle time. And unless your CPU is under contention, Brett mentioned that your CPU is basically load balancing across itself every 2 to 40 milliseconds. So you have to think, it's looking and doing transparent page sharing basically every 2 to 40 milliseconds because it's naturally going to have idle time. So yes, there is CPU overhead. No, it doesn't affect you because it happens during idle periods. And Brett, did you have anything to add?
I'll just point out, transparent page sharing is currently intra-VM exclusively right now by default. And we don't get into this in the session, but you can mess with something called a salting setting that will determine whether or not you can have inter-VM TPS. So when I say intra-VM, one VM can share memory pages amongst itself. That's not very efficient. You're not going to see big gains from it. Generally, I would argue that you can leave transparent page sharing as it is, which is effectively disabled from a performance standpoint, in my opinion, when it's intra-VM. The use case where I always want to test it as inter-VM is if I'm running VDI workloads.
Preach.
because you can get massive savings, and it's like just getting gigs and gigs of free memory. I mean, you can run them way oversubscribed when you've got 100 VMs on an ESXi host that have 4 or 8 gigs each, and they're all running the same identical workload.
Same set of applications, right?
Yeah.
Things like that.
Yeah.
A quick follow-up question would be, how can I see what my savings could be or what they already are for?
In ESX Top, it's listed above the ESXi host, above the black bar or the white bar, depending on how you've got your contrast set for the screen.
At that like high overview level, it shows you what the maximum is.
There's a metric up there that says shared. Is that what it says, shared?
Yeah.
P-share, thank you. Yeah. P-share is the metric, and you can see how much is on the host. I've seen VDI workloads with obnoxious savings. I mean, 256 gig ESXi host with 400 gigs of memory allocated and still not running in contention, running at like 60, 70% utilized. I mean, it's extremely rare, but that's a use case of how much it could play a part. Inter-VM, that's why we have intra-VM enabled by default, because the security implication is that hash that gets stored in memory can be violated. So it can be, the hash can be compromised and data can be extracted from the hash. Otherwise, for security purposes, ESX Top is constantly relocating memory pages in the physical RAM space so that if someone was to do some kind of surface attack on the memory, they never get the same page twice. But if they scan the hash table, they get the same page every time.
And kind of to give you a little bit of historical background, pre-vSphere 5.5, it was enabled across the host. So it was, you could just share across the host, and that's where we would start seeing a lot of performance gains, if you will, and a lot of space saving. But because of some security implications, basically there's a white paper that got published about doing exactly what Brett described.
Because it sounds like you're losing a lot of performance by not having this enabled potentially, right? But here's the thing. Your ESXi host is going to issue memory pages to the VMs based on what they request. Any modern guest OS is requesting large pages. Remember Rebecca talked about 2 meg pages versus 4K pages? 4K pages are small pages. Almost every virtual machine you're running now is taking large memory pages. Transparent page sharing doesn't work on large memory pages. Okay? So that's a big part of why VMware also made the decision to say we're going to just do intra-VM by default now because there's not a whole lot there. Yeah. Anyone else? Any other questions? Yeah, we'll make this the last, can we just make this the last one? Thank you, sir. And then anyone else, you're welcome to come up and I'll keep talking to you in the hallway or whatever.
I was just going to say earlier you mentioned that we should be trusting the VMs more than the hosts.
Not always.
Okay.
Rebecca's got trust issues.
It depends on the metric, right? So when you're looking at, for example, for memory, is when that was obviously said because I was the one that said it. When you're looking at active versus idle versus free, you have to think your virtual machine and the guest operating system may have 10 pages of memory, if you will, that are being actively used right now, and then 2 milliseconds are idle, and then 4 milliseconds after that, they're not being used at all anymore and they contain no data. Your hypervisor does not automatically just take it right back, because that would actually be more self-defeating because that would consume more resources to do so. So in that case, if you're really wanting to dive into active versus idle versus free, the more accurate source at that point would be the guest operating system. For everything else, you want to trust the hypervisor more. The hypervisor knows its resource utilization better than the guest. Yeah. All right.